over k. Then, so it's some statement about rational points, and it's that the rational points of x are covered by the rational points on y. So you take rational points on y, you map down by pi, and this is not quite true yet. You have to also include some twists of y, so it's a union over, I'll explain this in a moment, but for now, just understand it. So pi, let's say, gets a superscript sigma, and y also. So it means that you take y and a few other associated varieties, and their rational points cover the rational points of x. Okay, so this leads into torsors. Okay, so a torsor is, well, it's just a name for a principal G bundle. That's really all it is. It's another name for principal G bundle. And what is a principal G bundle? Well, first, what is G? And one can develop the theory in different levels of generality. So let me stick to linear algebraic groups. Okay. Then a torsor, so, well, it's a space, so a variety. I mean, again, I'm not doing things in maximal generality. You can work with schemes if you like, but let's consider varieties. So it's a variety with a G action. So it's a variety. And there should be a projection map to x. And the action should be compatible with a trivial action here. So it acts on fibers. And the action on fibers should be simply transitive. And there should be an additional requirement, well, some sort of a local triviality.
So do you mean it fixes the fibers and acts just on the fiber itself, or do you mean it's moving the fibers?
I mean, it acts, so if you start with a point in one fiber and you act by a group element, you land in the same fiber. And you can hit all the points in that fiber, and each point you hit exactly once with one group element. So each fiber is a copy of G. So if you're thinking geometrically, you have copies of G. Although the story gets more interesting when you have, as we are, we're over a number field, so you have all sorts of arithmetic complications. So this is really true about geometric points. For instance, y might not have any rational points. But so this is a statement about geometric points, and then there's a local triviality requirement, which says that it's locally, in a suitable sense, a product with G. So that's a simple, so a trivial G torsor would just be product trivial G torsor. You just take X cross G. So this should be a local model for the torsor, and local for the, if you know it, a tau topology. Okay, so that's something, well, it would be too much of a digression to define Grothendieck topologies and the whole theory, but you have to use it. And in fact, in today's lecture, we're going to see some cohomology groups that are étale cohomology groups, and again, it would be too much of a digression to do too much of the theory, but the cohomology won't play a major role in the lecture. So if you're not familiar with it, then just put it aside for now, and at some point you'll learn étale cohomology, and then you can make sense of it. Okay, so examples. Well, of course, trivial G-torsor is an example. If you have a vector bundle on X, then there will be an associated principal bundle. So if your vector bundle has rank n, then this will be a principal GLN bundle. Okay, so I warned you there would be some cohomology, and torsors up to isomorphism, so up to G equivariant isomorphism. Are classified, yeah? Right, it's a frame bundle, exactly. The associated principal bundle is a frame bundle. Oops, what does this say? Classified by a cohomology group. And it's so this is some non-commutative H1. And this is really more theory than I want to do. So from now on, well, okay, when G is commutative, then this is just the usual cohomology. So let's assume from now on then this is the étale cohomology group. So G, well, it's a given group over K. So you view it as a sheaf of groups, and then this is kind of, well, yeah, I warned you there would be some étale cohomology. So this is such a group. Okay, so let's consider now G is exactly, well, it's a linear algebraic group, and now I've insisted on it being commutative. So it's not group cohomology. So group cohomology is H1, G with coefficients in some module. So this is group cohomology. And étale cohomology would be H1 of, and then here you put some scheme like X, and then here you put some sheaf. So you can have a general étale sheaf, and in this case, you're taking G, the group, and you're viewing it as a sheaf of groups. So the sections over some u are exactly the g-valued maps from u. So you have all maps from u to g, and you add them using the group law on g. So g gives you, but you can also put here other kind of sheaves. And so, yeah, some. Okay, so G is now a commutative linear algebraic group over G, and let's over K, and let's consider a torsor. Now I want to make sense of these twists. So suppose sigma is an element of so now, okay, what is this that I've written here? Well, you can view K as a scheme, spec K. It's a point over K. And then it has an étale topology, and so this is an étale cohomology group. But that's the same as Galois cohomology for the absolute Galois group of K. So this can be identified with a Galois cohomology. So this is an instance of what we've seen in yesterday's lecture. Okay. And then what you can do is, so we have X spec K, and let's just for now call this map P. Just X is a K variety, so P is what I'm denoting it by. Then, let's see, so, yeah, what do I want to say? So we have sigma in H1 of Kg, and so we pull it back. To P upper star sigma, that's in H1 xg. And now the point is that this is, oh, I did exactly the thing I hoped I wouldn't do, which is not be completely absent-minded and exactly. So I apologize, and this is just me not being very careful. But when I wrote down non-commutative H1, this is a, well, it's a pointed set. So the thing I wanted to point out is that when G is commutative, then it's a group. Then this is an étale cohomology group. But in general, it's only a set. It just tells you isomorphism classes. But you can't, like for instance, vector bundles would correspond to H1 GLN. And now there's no way to add two vector bundles of rank n and get a third vector bundle of rank n. It's a set, not a group. So I apologize for just not being alert. And okay, a pointed set just because there's always a trivial G torsor, so there's always a trivial element. But that's really the structure that it has. Now, when G is commutative, then it's a group. And so you can add. You can take one G torsor, another G torsor, and add them somehow and get a third G torsor. And so that's what I want to do here. I want to take this G torsor, and I want to combine it somehow with, well, it's an element of H1, so it corresponds to a G torsor. And maybe instead of adding, I'll subtract. So take Y, whose class is in H1 xg. P upper star sigma is also in H1 xg. So their difference is in H1 xg. Since G is commutative, this is a group. And so we have an element of this group which corresponds to some G torsor Y sigma, of course, with a map to X. And so if this is pi, then this should be, this is just notation now. Oh, am I not consistent about, yeah, sorry. Everything is sort of ending up in the wrong place. But this is pi sigma. So this is just notation. That's all. So this is now a new G-torsor. Okay, now.
So somehow you use the first sigma. So use the first 2.3 from the notation.
P is only just x over spec k. That's all P is. It's only used just to say, well, take something here and pull it back to here.
Is there no naive way to say what y sigma is and with psi sigma as far as like the theorem goes that the rational ones are covered?
Yeah, I haven't gotten to that yet. I'm gonna.
Okay.
Yeah, let me. Yeah, so.
We take sigma and it's 1 of kg. It should be the homology.
Sorry, I probably. What should it be?
It should be well homology with coefficients in which one?
With coefficients in G of k bar. Yeah, this is minus. So this is some element, and this is instead of plus, it's minus. Well, it's a convention. That's it. Yeah, that's just the definition. But so the reason for it, I mean, you have to have a minus sign somewhere, and so let's. Yeah, I'm trying to avoid non-commutative cohomology. I mean, there are such operations, but anyway, it's too much beyond the scope of the lectures to do. Yeah, you have limited operations with non-commutative cohomology. So anyway, just to get that statement there. So let's say x is a rational point. So then you can restrict, what do? You restrict the given torsor, pi, to x. So you restrict, so then the restriction is a G-torsor over k, so it has a class and if how should I add it? So this has a class, so call it sigma then. So this explains why I took the minus sign here, because then you have y restricted to x, the point x is class sigma, and we take this element sigma, and then you have here sigma minus sigma, so you have 0. So then if we do pi sigma minus 1 of x, then this is the 0. This is sigma minus sigma, which is 0. So it's the trivial G-torsor. And so it has, well, points. at least we can be confident that it has identity element. So it has at least one point. So we see so it's the union of all
all the torsors are the trivial torsor, or should depend on the action of G.
Sorry, in what context? All torsors trivial?
Suppose that we're working with torsors over a spec of K.
Over spec K, yeah.
All the torsors will be trivial, or it depends on the action.
No, the torsors, you have a whole group of torsors. You have this many torsors. So depending what G is, this might be big or it might not. So
So it depends on the existence of the rational points on the torsor. The torsor is trivial if and only if it has a k-rational point.
that's right. Yeah, if you have one rational point on the torsor, then you know it acts simply transitively. So you can identify that with the identity of G and identify the whole torsor with G.
Is there any analog result for the general case torsor over some k, like some x?
Well, yeah, again, trivial if and only if there's a section, because as soon as you have a section for the same reason, you can identify. So maybe I should just do a very simple example, which is if G is mu2, so group of order 2, then essentially this corresponds to quadratic extensions. And a torsor over X. So then if you have a G torsor Y over X, at least locally, looks like you're adding a square root. So what X is maybe defined by some equations, and then you, in some variables, say x1 through xn, and then you adjoin something like y squared is some function of. So this would be an example of a torsor, and then a twist. And this d would exactly correspond to the quadratic extension square root of d. Okay, and what's known, so back to this general statement. So there have to be, I think, assume x is projective. Then only finitely many sigmas occur. So what should I say this? Then the set of all of these so it suffices to take a finite number of torsors. So Why? I mean, it's a theorem. It involves, it uses the fact that we're over a number field, and then you can find a model of X. Now let's see, do I need smooth? I might need smooth. I should have, an example, so, okay, this is bad. I should have checked. I'm sorry, I didn't prepare adequately for this lecture, so I don't know if you need smooth. Maybe I'll find out I probably won't find out this week, but if I write up lecture notes eventually, I'll try to get some statements that are correct, but even so, I think there'll be mistakes. So I'm sorry, it's just, lack of preparation on my part that I don't get the statements correct. Okay, so we had some statement from last time, and we had some exact sequence like this. So, this is maybe not very good, but so I had a bunch of hypotheses. So X was smooth, projective. And then I had Brouwer, X K bar, 0. And then we had this. So then there's something called Brouwer-Mannon obstruction. Which I talk about tomorrow. But the basic idea is that when the Brouwer group is non-trivial, when the Brouwer group of X is more than just K, there's at least a potential for some obstruction to the Hasse principle or to something I'll discuss tomorrow called weak approximation. So this also I'll discuss tomorrow. So then, anyway, but maybe we don't know what it is. We don't want to know. You just want it not to be there. So one approach to studying questions about rational points is to kill the Brouwer-Mannon obstruction by killing, if there is no Picard group, then there can be no Brouwer-Mannon obstruction. Okay, so this seems to be the lecture of unpleasant hypotheses. So in addition to those hypotheses up there, let's have one more. So let's assume that the Brouwer group of X, let's assume that the Picard group, geometric Picard group, is finitely generated. Okay, so then, so the point is, well, if we were in a geometric setting, then you can kill the whole Picard group by just passing to the, well, what each line bundle has an associated principal bundle, which is just the complement of the zero section. So. So line bundle is vector bundle of rank 1. So it's a GL1 bundle, that is just to say K star bundle, which is also denoted often GM. So if we take Li star, and then if we just take them all, so then this kills the Picard group. Now the problem is this is over the algebraic closure. So you want to have a suitable form of this defined over K. And that's where it brings us to theory of descent of Collio, Tollen, and Sansuk. So see how many accents did I forget? Here also? Maybe. I don't know. So, yeah, it's, these are two very good papers, so very foundational. So if you want to work in this subject, then you read these papers. So we consider. Yeah, I mean, yeah, sure. You can find out on the MathSciNet. I mean, this is in some conference proceedings, and this is in Duke Math Journal. So we consider groups of multiplicative type. So that's a fancy word. It means that when you pass to the algebraic closure, so you have some group S defined over K, such that when you pass to the algebraic closure, it sits inside some number of copies. So that's the definition. Over an algebraically closed field, you can have some copies of GM and some copies of the roots of unity, and then you have some form of it over K. So let's see an example. And I'll write it as a matrix group. So take the group of all elements x, y, and I think I want a minus sign there, maybe x, so like that. Over the rationals, let's consider. So this is the group of multiplicative type. You can see if you go to the algebraic closure, it's isomorphic to two copies of GM. But over Q itself, this contains an element of order 4. So it can't possibly be just copies Q star. This would not have any elements of order 4. So this is an example. Okay, so let S be a K group of multiplicative type. And then let Y to X be an S torsor. And then consider the dual group, which is Hom into GM. So this is a Galois module. And then we have a pairing and so we can now evaluate on Y so if you evaluate on Y, you get a map from and this map respects the Galois action. And so now part of this theory is to identify a special class of torsors, and those are the ones for which this map is an isomorphism of Galois modules. So, definition. The S torsor is universal if the evaluation map is an isomorphism. So this is also called the type. So the type of the torsor is an equivariant map of Galois modules, like so. So if it's an isomorphism, then the torsor is called universal. Now for a general type, there is an exact sequence. So type is from, well, I should have, as usual, I'm writing too quickly and not being careful. This map is not type. Type is the map that takes a torsor and spits out a map from a map of Galois modules. So type takes a torsor and gives you a map of Galois modules so this is type. Okay, and then the kernel is H1KS. And then there's some obstruction group. So you can start with the desired type, for instance, isomorphism. You can just take take S hat equal, pick xk bar, and then take identity. And then you wonder, does there exist a universal torsor? Or you start with some other type and ask, does there exist a torsor of that type? And the obstruction lies here in this H2 group. Now, yeah, I mean, there's all kinds of étale cohomology groups, Galois cohomology. I mean, this is quite fancy, so I don't want to dwell on this. But I just want to say that there are these groups, obstruction groups, and these groups that classify torsors. So just the features to take away from this. Well, we had somewhere on one of these blackboards, yeah, here, the finite collection of torsors whose rational points cover the rational points on X. And it's exactly elements of H1, K, G is now S. So that's exactly here. So you're taking all torsors of a given type. Take a torsor and then start adding to it elements of H1, K, S. And so this gives you the collection Y sigma. If you start with a torsor Y, then you get the Y sigmas there. And the other thing to take away from it is that suppose there is a rational point. So if X has a rational point, then this map has a splitting, the boundary map is 0, and so this type homomorphism is a surjection. So being able to find a torsor of any desired type is a necessary condition for the existence of rational points. So let me write that. So we see that surjectivity of this type homomorphism is a necessary condition for existence of rational points. And hence, for any lambda here, X of k is covered by the pi sigma of overall y. Well, what should I? Let me just not put that notation. I'll just. Okay. I hope the notation's not very confusing. So this is saying all y over x of type lambda. So all y, that is all torsors here, whose type is lambda, and take a union of all those. And then each pi, so pi is maybe I should write it like this, y pi x of type lambda. It's less confusing. And then rational points on y. I made a mess of this. So this is y to x of type lambda. So it's a sum over all y to x. So you've picked some lambda here, and you're sort of taking the pre-image here, except that this group classifies torsors. Of course, torsors up to isomorphism. But anyway, just take all torsors of type lambda. Because if there's a rational point, then you can evaluate. You have sort of x. A rational point is like a section. So you would have a map going this way. You could evaluate an element here at that point. So if you had a rational point, then this would have to be injective. Also here, it is injective, but this would be injective. And so in this exact sequence, this map vanishes, and so this is surjective. So to say it another way, if there's at all some lambda here for which there's no torsor of type lambda, some lambda here not in the image, then this map is not injective, so there cannot be any rational points. So it's just empty set. So we're covering the empty set by the empty set in that case. Okay, so let's work out an example. And let's do the example from 2 days ago. I had written down an equation. So I hope at the time I didn't say the wrong thing. I mean, I should have written, where does x live? It's in P2 to 1, 1, weighted projective space. I could have easily said something or written something different, but of course that's where it is. Okay, and then I sort of I gave as a hint something with about quaternion algebras. So, and then I hinted that has something to do with the Brouwer group, and so there's some Brouwer group element, and that's coming into play, making this a counterexample to the Hasse principle. So let's take this approach and just kill the Brouwer-Manin obstruction. Well, we don't know what it is yet, but just eliminate that group cohomology there that's giving rise to Brouwer group elements. And so we do that by writing down a torsor. So let's take y. So if x is defined by this equation, then take y defined by this equation and the additional equation here. So what's going on here is that you do some sort of some analysis to say that P, if you have some U, V, X, Y, rational solution. So let's take an integer solution without common prime factors. And then if you have some prime that's 3 mod 4, and if it divides both x squared minus 2y squared and minus x squared plus 3y squared, then it would have to divide x and y which in turn implies that P divides both U and V, and then you would be able to divide out a P throughout. So in essence, you have and then P, you use a little more of what we know from basic number theory. P divides the left-hand side an even number of times. So P divides the right-hand side an even number of times. But there's one of the factors that's not divisible by P at all. So P divides the other one an even number of times. So such P must divide this quantity either not at all, or if it does, an even number of times. And all that tells you that x squared minus 2y squared would have to be a sum of squares. So here we have a single y such that, so we have y to x such that pi of y, I didn't say, of course, over q. Pi of y of q is x of q. So this is an example of a torsor, and in this case, the rational points are covered, I mean, we need just a single torsor. In general, there will be a finite number of torsors, a finite number of twists. And here, you just need y itself. No twists needed.
Is it easy to see the geometric power group of this as trivial?
It's rational over the algebraic closure. It's rational. It's a conic bundle.
Sorry, so what do we mean by the two arrows in front of the y?
Oh, so y will be defined, so two more variables and the additional equation. So we add variables q and r, and we have this additional equation. Well, everything is up to sort of birational. In fact, I'm going to write down a different birational model of y. So in fact, so a different So in fact, you can take q squared plus r squared, and yeah, so this is that houses. So now this pi map sends so u is I don't know, what is it, qs minus rt, and d is qt plus. So you should think of this as saying that the norm of q plus the square root of minus 1 times r is this quantity, and here the norm of so it's like this is a norm of something, and the product is a norm of this. So there's, in a sense, another factor whose norm is this other quantity, and then just think how would you multiply q plus square root minus 1r by s plus square root minus 1t. And so anyway, this is you can verify this. So this is a birational model of y. Sorry, I didn't catch you. The local cases of what?
The cohomology group, which is in y-junction with all of the principal G-bundles.
Yeah, so the H1.
Yeah. So we could consider it over the completions over other places.
Yeah, you should have been here just a few weeks ago. We had the Emmy Noether professor. We had Paramala, who gave some beautiful lectures on exactly this theme, on sort of if you have a torsor for a group G and you know that it's trivial locally at all completions, is it trivial? And in fact, it involves a number of deep questions and exceptional Lie groups, and it's a research question. So this is two-adically obstructed. So why? And this you can just see. I mean, it's easy. You'd work mod 4 or mod 8 or something. There's nothing. So. Okay, and maybe I can just say that. So it's a very simple example, but and it uses a very small torsor. We've gone only from dimension 2 to, and it's Winterton-Dyer in '87 to completely study the existence of rational solutions to equations of the form and so they have essentially complete results about when the Hasse principle holds or what sort of obstruction there is, Bauer-Mannen obstruction. And this is also a very good, very important paper. So I'll stop there.